very broadly, like hard and easy, easily solved, can be done quickly. For example, sorting. If you sort a list of numbers, a computer can do that quite quickly and easily. That's an easy problem. But say you're the only computer science guy in a school, for example, high school, and so the headmaster says, "Oh, please write a computer program to schedule classrooms for the whole school." You'll very quickly learn that scheduling is a very difficult problem for computers. That's a hard problem. And so complexity theory talks, it asks the question, what is it about the scheduling problem, for example, that makes it so much harder, time-consuming and difficult and lots of calculations needed, compared to, say, a simple problem like sorting. Okay, so this is it's very practical. Like if you're a practical computer person, for example, if you've studied or studying a computer science bachelor degree, then speaking as a former computer science professor, let's say the two main skills that you pick up at undergrad level computer science, one is just programming, right? You learn how to program, and that's probably how you'll be making your money if you go out into the commercial world immediately after a bachelor's degree. So learning how to program, you're learning how to think to be able to program, because it's a special way of thinking. You have to tell a computer what to do. You have to tell it everything, so you have to think it through in a very tight, logical way, and that computer programming fosters that kind of thinking in programmers, the people, programmers' minds. And I suppose the other main skill for computer science is techniques like data structures and algorithms and that kind of stuff. There's sort of two basics of computer science that are taught. Now, as part of like learning algorithms and data structures and stuff, then complexity theory might be a part of that, because you'll learn there are various categories of types of problems. There are differences in the levels of hardness, why some programs like hugely difficult compared to others, but both are still hard compared to the easy ones. So complexity theory gets divided into various categories, different types of hardness, of level of difficulty to solve various problems. Now it's the third part, so we won't get onto this for quite a while, but and they're in a sort of logical order. You need to know in a sense you could say this is the what. What is computing? What is it to compute? And this is once you know what it is, this second part asks the question, what can be computed? Once you know what computing is, well, what kinds of things can be computed? And once you have the answer to that, this third part, I guess it's more about efficiency. How can things that are computable be computed easily in terms of efficiency? Like you can take a given problem, for example, and you might try a particular approach to solving it, and it works out to be very difficult. And then you rethink and you change the approach to solve the problem, and then suddenly it becomes much easier, taking hugely less time. So doing that kind of thing would be part of complexity theory. All right. Okay, so the 30s, when this really got going, people like, initially say Gödel, and later especially Turing, Church, Kleene, that's K-L-E-E-N-E, People like that. All right. Okay, so what's automata theory? So what is an automata? Well, it's sort of another name for a machine, but it's a computing machine, a machine that computes in some sense. I'm being deliberately rather vague. So this part here, automata, it'll define various kinds of automata, machines that compute in a vague sense. There's like here's one automata type, the so-called finite automaton. The automaton is the singular, and the plural form is automata. Automaton, automata. Ta is the plural. Okay. So another kind of automaton, if you like, is the context-free grammar. Well, you can probably guess from the label itself. But what's a grammar? We'll talk about this at length. This part is giving you the tools, the definitions, the ideas on how to compute. What is it to compute? What does compute mean? This kind of stuff. So this is a sort of preliminary stuff. It's the what part. Okay. So what is computation? What is a computer or an automata? Okay. So this part, these few early chapters will give you the conceptual tools, the ideas needed to for the later part. Once you know what a computer is in terms of a machine, what it does, then you can use that knowledge to ask the main question of part 2, the computability theory part, to ask the question, what can and cannot be computed. Okay, right. So now computability theory. I already talked. Probably go through this fairly quickly because I've already talked about it quite a bit. So here are some of the big names in computability theory. Gödel was his primary interest was in the foundations of mathematics. He was a mathematical logician. Like I was saying, one of the best ever lived. Okay. So Turing, for example, Gödel found with his incompleteness theorem, I was saying a bit before, that there are statements in mathematics that are not provable given the axioms in that branch of math that you're talking about, the statements within the context of that branch of math that has that set of axioms. And Turing was inspired by Gödel's stuff, and Turing found, with his famous halting, H-A-L-T, to halt means to stop, and his famous halting problem, well, I'll say a little bit about it. The halting problem is the following. Can you find a piece of software, can you have a computer that into which you put some computer program, and the question is it possible to have a machine which itself is programmed, so a general machine that can tell yes or no whether the program that goes in will halt or not? Will it stop? Will it be computed or not? And that's the halting problem. Will it stop or not? And Turing proved that there's no such machine. It can't be done. It cannot be done. Right? So, so basic idea of computability theory. One of the essential ideas is some tasks, some computing tasks, cannot be done. They're just impossible. Right? So, like for example. Like here's a question: Is a mathematical statement true or false? Right? Seems innocent, simple enough question. Okay, And that's sort of the bread and butter of mathematicians. They're doing this all day. But there's no computer algorithm, there's no computer program that can answer that question. Right? The halting problem is an example, and that's one of the examples that Turing discovered, the famous Turing halting problem. Right? So talking about this stuff, it motivated people on the theory of computation, and once that became more clarified, it led in turn to the creation of actual physical, engineered, hardware computers, real machine computers, right? To real practical computers. So in a sense, Turing played a major role in providing that motivation, right? Because he did a lot of the theory behind the understanding of how to compute, how to build a machine that could compute. His elementary toy computer, computing device, the Turing machine that we'll definitely talk about in detail, was an example of a machine on paper, a toy machine that motivated the creation of a more practical, faster, more efficient version of the same idea. In other words, a hardware machine. And so, in a sense, he's sort of the father of the computer industry. Okay? And complexity theory, I'll talk quite a bit about that. It's connected to computability. In a sense, it's a subset of computability theory, right? So complexity theory, you take those problems that can be computed and you classify them into various levels of difficulty in how to solve them. Some problems are harder to solve than others, and some are very hard, and some are less hard, and some are just hard, and some are almost impossibly hard, and so on. So we'll talk about complexity theory much later in the course. It's part 3. Right? Well, that's the end of this session. I'll stop there, and I have to change the camera angle to do session 2, the second quarter.